happening. So I want to talk about like some very long project which like maybe started before I was born, depending on like who do you ask. It's a little bit strange to talk about something where like one of the co-authors is like passed away about like several years ago, and I don't think I have ever had a chance to talk to Akush about like any of this stuff, or like actually about any math ever. But I'm sure like he mentioned like this problem to you or to some of you like a few times, and like he worked on it like for a long time, like definitely like since mid-90s or something. Okay, so in some sense the starting point for me is like a project we did with Bill Cantor, Bob Graunik, and Tarek Slobodsky about like 15 years ago or maybe 10 years ago, I'm not sure, depending whether you count by like when we proved the result or when the paper was published. And it was like reasonably nice and very surprising result about presentation of finite simple groups. So what we managed to prove is that like all finite simple groups, with possible exceptions of like the small V groups, have a presentation with say 2 generators and about like 100 relations. And if you want, you can actually modify this thing a little bit and make sure that like all the relations are very short, or at least surprisingly short. Okay, so a couple of comments about this thing. So first, this really uses the classification of finite simple groups. When we started, like my interpretation of the classification is that like there are essentially 2 families of simple groups. One is symmetric groups, the other is like SL and FP. Anything else is like a technical nightmare. And I was mainly like thinking about these 2 cases, and like other people like Bill Cantor like essentially said, well, okay, if you can deal with this thing, we know how to deal with the rest. So they spent most of the work like doing the technical nightmare stuff. And like one of the problems was like, well, this kind of technical tools like works for most of the things, but not for everything. And there are a few exceptions where like you need to be a little bit careful. And like these exceptions are like mostly rank 1 groups where things are getting quite messy. So some applications of this thing. Okay, I'm not sure whether these are real applications. The first one is like this gives you a really nice way to completely finish all the bounds, like we start from Babai and Cantor, of like estimating number of isomorphism types of groups. Like inside this proof, like it's relatively easy to see that like the most count comes from like P groups, but like in order to prove this thing, you need some kind of relatively weak estimates for presentations of simple groups. I think you need to estimates which are much, much weaker than that, and which were known like way before that. So that's not really a nice application. Another application is something about like estimating dimensions of cohomologies, which like this directly related to presentation. You can replace like here simple groups with like more or less arbitrary groups, but like you have to be quite careful what kinds of bounds you put. And the third application, which probably is like the most important one, is like you can use these presentations for like some kind of algorithms for computation with finite groups. And like Iman is like very keen on this thing, and he has been bugging me for the last 15 years that like we really didn't do anything because our presentations are not useful for him. And the reason they're not useful is like he refuses to read the paper. Like, for example, last year he came to me and said, well, somewhere on this page, like you need an element with this property, and like I really want to know how on earth like you prove the existence of this element and like how to construct it. And I said, like, come on, guy, like I haven't been looking at this paper for 10 years. Let me go back to it and like see what I can tell you. I opened the paper and like there is an appendix with a lemma with an explicit form of this element. So I just point this thing to him and say, okay, like go from there. Of course, like clear there are a bunch of typos in what we did. So like some of like our presentations might not be exactly right, but like they're more right. I think things are getting fixed by now, but like Iman is like still not very happy with what we did. Okay, so what I'm going to talk about is this project, which I think it was started by Alexander and Arkush, like probably in the late 90s, to figure out what's happening with the rank 1 groups, and like we are able to finish it like this year, like actually a couple of months ago. That like the only exceptional case, like the so-called small regroups, they fit into the same picture. Like you also have like the same kind of presentation with the same kind of properties. So in order to like make anyone happy, I just could say that like actually you have a very natural presentations. You have to go to some kind of completely crazy generators and completely crazy relations. Okay, if you go to the natural generators and relations, like you probably need like something like logarithm of Q generators and about like logarithm of Q square relations. However, there are like completely standard tricks which make the presentation a little bit more messy, and like you can actually reduce everything to a bounded size, bounded number, and like relatively short size if you really want to do this thing. So for people who actually want to use it, the actual presentation is relatively easy to say what it is. What you do is you take a presentation of the Borel, you take the presentation of like twisted G2 over like the field with 3 elements, and like you identify them with over the obvious things, and this is actually going to give you a presentation. Okay, maybe you have to add some kind of other semi-obvious relations, like say that like the vowel involution, like invert the torus or something like that. But like the things are completely obvious, like what you have to do. Okay, so it took me a while to get to this kind of problem, and the reason it took me that long is I really hate doing any form of geometry, and there is no way you can do anything with rank 1 groups without going into geometry. That's completely impossible, and I always assume that like the things which are done by Suzuki for the Suzuki groups or by Serge and Hupke for like SU3, I always treated them as complete magic and say like they did this magic and like the result pop out, and I'm not going to understand this magic, so there is no way I'm going to generalize it. But it turns out that like actually the magic is not that difficult, and it's actually quite natural. Of course, there are like a bunch of technical details which I'm going to skip at some point, and I'm not going to get that much into them. Okay, so what's the geometry you have to deal with it, and like why things are like relatively natural, at least up to a certain point. So what I'll try to do is like give you some kind of like uniform idea how to deal with like most of the rank 1 groups. So the proof I'm going to give you, of course, like it works for PSO2. It's essentially going to work for Suzuki. I'm going to mention like what you need to check for the Suzuki in order to work. Most of this proof like somehow works for SU3, but like not exactly. SU3 is a little bit more special, and you need to be slightly more careful how to do it. And the reason is if you want to build a presentation for SU3, you have to be very careful how to choose the generators and like which relations you pick. You cannot really have that much freedom in this case. It's like pick whatever you want and it's going to work essentially. Okay, so we're talking about some nice rank 1 groups, and when you do have a rank 1 group, there is a lot of like geometry and structure like coming out of it. So one of them is the Borel subgroup, which is like a semi-direct product of torus and the unipotent part, and you have a vowel involution. And the main thing you know is that the group is essentially a disjoint union of like 2 sets. One is B, the other is BTB. So like this is kind of like Val decomposition of groups, like you just like go over the elements of the Val group, which in this case has 2 elements, and you take the double cosines with respect to B. Okay, so now what this thing implies actually for rank 1 groups. You can start with any element in U. You can conjugate it by T. So what you're going to get is an element in the group. And since this is an element in the group, it's either in B or in BTB. Okay, obviously it's not in B, because like if it's in B, things are going to get like a little bit stupid and the whole group is going to collapse. So you can write it as an element in B and an element T and another element in B. B is like H and U, so like you can move things around. And what you can get at the end is that like you have 3 functions. 2 functions are from U to U, or technically from U minus the identity to U minus the identity, and the other is like a function from U to the torus. So that like T of T is equal to L of U, T, H of U, R of U. And like you have a freedom, like you can put H on the other side of T or whatever, it's not going to make any difference, like that's essentially the same thing. And this thing is called like a Steinberg relation, because like of course like this is like goes back to Steinberg from the 50s. And there is like this kind of like very classical result, which is like in some sense completely elementary to prove, is that like the group has a presentation which is like extremely natural. You take a presentation of the Borel, take a presentation of the normalizer, and like you add all the Steinberg relations for all elements in U. And that's what I'm going to use, because like if you want to prove that something is a presentation of a given group, usually you have to at some point like do some kind of a writing system, or like eventually show that like every element can be written to some basic form out of like what you're given, which becomes very annoying, and like this like actually takes care of this. But in this case, like the writing system is very easy. Like the Steinberg relation essentially tells you that like if you have expression which involves 2 T's, you can like rewrite it and get only 1. So eventually you can reduce the number of T's to 1, and this gives you essentially a presentation of the group. Okay, so if you want to use this thing, so you have 3 ingredients you have to deal with this. You have a presentation of B, presentation of N, and the Steinberg relations. So the presentation of B is probably the easiest, like depending on what you want. U is nilpotent group. It's in the case of the Lie group has like size like Q cube. So it's essentially trivial to write a presentation with like logarithm of Q generators and logarithm square of Q relations. Essentially what you do is like you take a decomposition series of the P group, like with the factors of, with the second groups of order 3, you pick one generator for each of them, and you more or less like build the multiplication table on them. And that's what this thing gives you. And like, of course, I'm dropping all the constants. I'm not going to deal with like 3 logarithm of Q and all this kind of stuff. Okay, once you have a presentation of U, you just put like the torus on the top of it. Like the torus like is a cyclic group, so like you don't really have any issue about like building a presentation. You don't really have any trouble like describing the action of the torus on U, at least like modulo like adding a couple of relations. So it's not really going to change our count at that stage. Now, if you want to optimize things, there are actually like reasonably standard tricks which goes back to like bounce work or like Campbell, Williams, and Robinson, which actually allow to use like a bunch of other structure, like the fact that like you're working over a field and like things are a little bit more consistent. Like your group is like essentially algebraic group scheme or something like that, so you can express everything in a very short way. And like you can get away with a bounded number of generators and relations for B. Okay, so this is something which is like not completely trivial. It requires checking some stuff. And when we had this project with Bill, Bob, and Alex, we checked this thing, but like the check was based on like some computer code which I wrote, and I'm really a crappy programmer, so don't trust anything I wrote. and like it was never like really verified. And like there is something which needs to be verified for this kind of thing to work. It's not like absolutely automatic that when you have a system like that, like you can reduce number of generators to a constant thing. And we haven't had the chance to like completely verify this thing, but like I'm pretty sure it's going to be okay. Another comment is that like you can make everything like reasonably short, but here you have to be a little bit careful. Like the Borel subgroup is definitely not simple. So it has a very large abelian quotient, so it's not even possible to construct a presentation where you have a small number of, like bounded number of generators, bounded number of relations, and every relation is extremely short. Simply that's not possible. What you can do is you can get such presentation of an infinite central extension of the group, and that's enough for like most of the purposes. But I really don't think anybody is going to try to use this thing in practice, because my estimate is that the number of relations you need is going to be of the order of like probably 500, maybe 1,000. So unless you deal with Q of the order of like 70, like it's much easier to just go and like with the standard presentation. And I don't know like what kind of computation like people like Iman are doing, but I'm pretty sure they cannot handle like Lie groups of size 3 to the 70. That's like pretty big for like any practical purposes. Okay, so where is the geometry coming from? The geometry is coming from that like the rank 1 groups have like a nice double transitive action on something which like it's like in the case of SO2 like called a projective line, otherwise it's called like an oval or over it or like whatever it is. It's some kind of nice subset of the projective space of certain dimension. In this case it has like q cube plus 1 points. So in general you have like 1 point for each element in U and 1 point in infinity. And well, you know that like a stabilizer of a single point is like the Borel subgroup, and like usually you call it like this point infinity if you want to have a copy of the standard like B. If you have a stabilizer of 2 points, you get a torus, and U acts like transitively on whatever you have. Another thing you can see is that like when you deal with Steinberg presentations, you need to put one relation for each element in like each non-trivial element in U. However, you have a natural action of H, so like if you have relations for 2 elements which are conjugate by H, they are essentially the same, so you can drop one of them. It's not really going to be a big deal. So you don't really need to put like Q cube relations. You can get away with Q square. And that's some kind of like the obvious observation you can do. And this is something which is more than enough for like groups like PSO2, because like they're like the unipotent is 1-dimensional. You do this count, like you get like essentially 2, and like you are happy, and like everything is done. Here, like, okay, you made some progress out from Q cube. You reduce it to Q square, but like it's still like pretty big distance. So like it's not completely clear how to proceed from here. Okay. So the next thing is some kind of like standard observation, which I'm sure like Arkush knew it. I couldn't find it in like any of the papers like he wrote like with him and Alexander. I'm pretty sure it's somewhere in the literature, but like I had to actually spend some time like to discover it. And this is the fact that like the Steinberg relations are very far from independent. They actually comes in groups of 6, and like in some sense like there is a natural action of like S3 on them. And the reason is if you have the Steinberg relation for an element U, you can just invert everything and more or less get the Steinberg relation for like U inverse. So these two things are mostly equivalent. The other thing you can do is you can think of the Steinberg relation as like having a product of element B, T, B, T, B, T equals to 1, if you move everything to one side. So it's like some kind of like product of three things equal to 1, and you can permute them around. You can rotate them, like you can by doing some conjugation and so on. And this essentially tells you that like if you have the relation for U, you can get the relation for L of U and for R of U. And you can say, oh, why can I extend this thing forever? No, you cannot, because like you can prove that like these two operations are more or less like they more or less commute. If you do the inversion and like apply L, this is the same thing as like applying R and doing the inversion or something like that. So eventually, you're going to get a nice something like S3 action. Okay, so that's not really very surprising, but like if you try to deal with this thing from completely algebraic viewpoint, so you treat L and R as like some complicated rational function, this thing starts getting like very annoying. Like you have some rational function which is given by like quotient of polynomials of degree like 3, 4, 5, depending on how you count, and like it happens to be an inversion. Like that's not really something which is like happens all the time, and like you want to understand it in like a little bit more geometric way than saying, well, this is what happens. Of course, like this is something which is extremely useful to verify all your computer computations. Whenever like you have something which like is supposed to be your function L, you just check it here and like say, oh, okay, like if it doesn't satisfy this property, there is some typo somewhere, and you really need to double check all this kind of stuff, because like different people who have worked with regroups, they have like different ways to put coordinates of U, different ways to put coordinates of the torus, different ways to like define what is like the field automorphism. So you have like 3 or 4 different formulas, and like they look similar, but they're not exactly the same. So my advice is like never copy any formula from the paper until you read carefully the paper and know exactly what they're doing and that it applies to your situation, because like things are like a little bit off from time to time. So it took me a while to figure out what is actually happening and how I can like understand this action in some kind of like natural way and to get something out of it. And what I realized, and like let me know if this thing is well known, because I assume it should be well known, but like as I said, I'm not geometer. I barely know anything about like rank 1 groups, so that's not something which I can say that it's really new. What you can see is that you can identify the classes of the non-trivial elements in U modulo the action of H, essentially as like triples of points in O modulo the action of the group. Okay, of course, like you have to make sure that like your points are distinct, so you have to remove some kind of diagonal and stuff like that, but that's not really a very big deal. And the proof is like essentially obvious. Like if you act on triple of points, the group is like doubly transitive, so you can make sure that like you send the first and the second to 0 at infinity. Okay, so the third point you can identify it with non-trivial element in U, and then like the stabilizer of 0 at infinity is H, so that's exactly what this thing is. But O is my projective line, or like ovoid, or whatever you call it. And the fat diagonal means like distinct points. And now here, like you actually see what is the S3 action. You have a very natural S3 action on our cube by permuting the coordinates. You double check that like it's exactly the same thing. Of course, depending on like how you identify like U with like the cosets, like one of the elements is going to correspond to the inversion, the other is to L, the other is to R. Like you have to be a little bit careful with this thing, but you know, there are some choices you have to make, but like they're not making a huge difference. Okay, so this is some kind of like more or less like general understanding of the setup, like where we are going and like how to work with this thing. Now, oh, sorry, okay, I forgot about this thing. Here is something which I'm sure like really Arkush discovered on his own, but like something like this is actually in the Suzuki's paper, but it's really hidden there. Like when I started reading the Suzuki's paper, like I immediately sent an email to Bill saying, okay, like you said that like he's proving that like the Suzuki group has presentation with this kind of form. The word presentation does not appear in that paper at all. Like what's happening there? And he said, well, like if you read carefully, there is like this kind of argument on page like 63, which is half a page, and this is equivalent to this kind of computation, which like implies this thing. And I said, okay, sure, that's correct, but like I had to know what like I'm trying to find, and like so. So what is the observation? The observation is that if you have the Steinberg relations for 3 particular elements of the form u, v, and the product u times v, you can combine them to get another Steinberg relation. And how do you do this thing? You just write the 3 relations down. You notice that like t is an element of order 2. So if you multiply the first 2 of them, like the left sides are going to give you the left side of the other one. So you're going to get something of this form. And now you can just rewrite it a little bit. So move this thing to that side, this thing to that side, and essentially you're going to get like the Steinberg relation for like R a few times L of V. And everything is given by some kind of like nice messy formulas. If you start working with like regroups and like replace this thing with like the corresponding equations, this becomes like a huge mess, and like you cannot really do any computation by hand. Like that's one of the first things I noticed. So initially I was trying to like just like brute force this thing and like use this thing to like actually go somewhere, and then I realized that like I don't have an access to a computer which can actually deal with this thing in an efficient way. So I needed to figure out like how to view this thing a little bit. And then I realized that like this kind of geometric picture tells me how to view this thing. So what this construction is saying is the following. Suppose I have like 4 points on my ovoid, and I think of these 4 points like forming like a pyramid, and suppose I have the Steinberg relations for 3 of them, for 3 of the 4 faces. What this construction is actually telling you is like using these 3 Steinberg relations, you can deduce the Steinberg relation for the 4th one. And like you can actually like use the algebra to move from this picture to the other one, like they're like more or less equivalent, but this thing is a little bit nicer to look at it and like at least say, okay, now I can actually phrase my question in something like more geometric way. Okay, I have like relations corresponding to some faces, and I want to glue them together in some kind of nice way to prove something and so on. So you have some kind of picture what you're trying to do. Of course, eventually, you need to go to formulas and do some computations. There is no way of like completely avoiding doing any computations, but my first attempt of like just brute forcing everything was like complete failure. I spent like most of the almost an year trying to like force some computers to compute some Grobner basis of whatever I needed, and I think I was able to compute only 1 Grobner basis of like all these kind of things out of like maybe 300-400. So things are not really working. Okay, so what is the main observation like from here? So somehow you want to produce a bunch of elements where like you can deduce easily the Steinberg relation, which form of this kind of triple, such that like 1 element is a product of 2 of them, so that like you can start taking this process and like iterating it many times. And the observation is that like initially the only operation you have is the conjugation by H. So what you really need to do is you need to build something which is like essentially a subgroup which is obtained by conjugation. And there is like one very natural choice, and this is the center. The center is generically a subgroup of size q, which can be identified with like the additive group of the field, and moreover, like the center, the torus acts transitively on the non-trivial elements. So, okay, this is not completely true in PSL2, but it's like true in all the other rank 1 groups. Okay, it's a very easy computation to check it for the Suzuki groups and for the Lie groups. I believe that there should be like very conceptual proof that like this is the case. I don't know it, and I'm not sure like where this thing comes from. Of course, it's not a very difficult check. Like it's really something like some element is invertible, which like you just write down the inverse directly, so it's not a big deal. So what this thing tells you, this tells you that like if you take the Steinberg relation for one non-central element, you can actually get it for like many central elements, and using these many central elements, like they're closed under multiplication because like the center is a subgroup, so you obtain it for a few more. You compute what you get, and you see that like you manage to obtain about like q of the needed q square relations. Maybe q plus 1, I don't really care about 1. And like this is like explicitly in some notes which like Arkush had like from 15 years ago, maybe a little bit more, very explicit equation, what kind of things you can get from here, which classes, and so on. And there is one thing you can do, and like you say, okay, let's try iterating this thing a few more times, and like hope for the best and say that like things are going to work out. Okay, that's very easily said and like not so easily done, because like what you get is definitely not a subgroup. So like these q conjugacy classes, they are not closed under multiplication. Actually, it's extremely rare that like you can find like a product of two elements from these two classes to be another element of this type. So it's not so easy to do this thing. And like somehow geometrically and like using counting arguments, like you expect to have like many of these elements. But like when you put this thing in a computer, like you can see, okay, like I have like some kind of like two-dimensional like surface in the three-dimensional space, which corresponds to the like the relations which I know out of this thing. I'm looking for like triple of points such that like the product of two of them, triple of points from like this surface such that the product of two of them is equal to the third one. Okay, so this gives me some kind of algebraic variety. Let's try to figure out what's going on. Okay, I put this thing in a computer. I let the computer sit for like a couple of days, and like it cannot actually compute the Grobner basis of this thing. And I was like staring this thing for a very, very long time. And eventually I realized that like I don't really need a computer, and by hand I can actually see that like this variety is like rationally isomorphic to like a three-dimensional space. So this tells you like what kind of like messy equations you're dealing with. It was like I can actually do the computations like by hand, and like my computer cannot actually do that. And like there are many reasons for that. Like one of the reasons is that the number of variables like it's pretty big. So I think I was dealing with like polynomials in about like 15, 20 variables. The degree of the equations, they're not that bad. Like they usually start with like 6 or something like that. But when you start combining them, you immediately get to equations of degree 100, and like then like you cannot even read like what you're doing. Okay. So let's try to put this thing in some kind of like nice geometric language, what we are trying to do. And from there, we can see that like things are like somehow doable. So this is some kind of terminology which we stole from like some other papers about groups. Like of course people are dealing with like completely different type of questions. So they're trying to figure out like what kind of like structure you have to put on the over it in order to recover the Lie group as like the automorphism group of this structure. And what they defined is this kind of notion of a circle. And the circle is something which is defined by essentially a center. So you pick a point. This point gives you a standard copy of the Borel as the stabilizer of this point inside G. This Borel has a nice unipotent in it, and the unipotent has a nice center. So once you fix the point, you actually have a center, a nice group of order Q. Okay, so you say, okay, just take the orbits of this group and add this point to it. So a circle is essentially an orbit of the center together with infinity. And by more or less by definition, we are only putting the center, the Steinberg configuration corresponding to the central elements, and this central element corresponds to triple of points such that they lie on a circle, and one of them is actually the center of this circle, because that's how we define them. Now, using this kind of construction of saying, oh, if we have the relations for 3 of the faces of the pyramid, and we can get the relation for the fourth face, what you can see is that using this construction, you can actually get the relation corresponding to any 3 points on any circle. And this is really what I was talking about a minute ago, this kind of messy formulas you obtain by taking relations for the central elements, combining them together using this operation and getting this kind of big mess and complicated formulas. Okay, so what we want to do, we're given a triple of points and we want to deduce the Steinberg relation for this triple of points. So ideally, what we want to construct is some kind of a very nice solid or 3-dimensional space object with triangular faces, such that each triangular face is the 3 points y on the circle, so I can deduce this relation from the central Steinberg relation, and the last face is what I need to deal with. Okay, there are a couple of things I have to be a little bit careful. I have to put some kind of nice solid. I cannot really put anything I want, because my operation is not homological. I can only do it on pyramids, so I actually need to have my solid to be able to partition this thing into a pyramid in some kind of nice way, and this puts some kind of restrictions. So for example, I cannot really have octahedron or anything like that. But that's a mild thing, and so on. And now when you look at this thing and say, oh, that's surely possible, it was having 3 points on a circle is essentially one equation. So each point has 3 coordinates. I just put how many faces I have, how many equations I need to put, and eventually I'm going to deal with a system with I don't know, 30 variables and only 20 equations. Obviously this defines a 10-dimensional variety. It's going to have enough points. Everything is going to be completely fine. And that was what made me start it. And I said, okay, sure. It's the only thing I need to do is compute the variety and make sure that things are okay. But I quickly realized that there are some problems. Okay, what are the problems? The problem is first you need to deal with this kind of structure you have, and you cannot really use the standard algebraic geometry. And the problem with this thing is, in order to do anything, you need to realize that the regroups, they're defining it only over fields which have an automorphisms which is the square root of the Frobenius. So that's not a general algebraic geometry picture. You have to actually put it inside your structure. So you can think of everything as some form of a group scheme or whatever language you prefer, but you have to make sure that your schemes, they're not defined over all possible fields or link or whatever you're dealing with, but you need to actually also choose a square root of the Frobenius inside this picture. Okay, so this moves you a little bit outside standard algebraic geometry. My feeling is, okay, that's not a big deal. I can find somebody who knows algebraic geometry who can fix this kind of issue. That's the easiest thing to do. I'm not going to worry too much about that. And now, once you deal with this thing, yeah, okay, U is a nice unipotent scheme, like it's a three-dimensional, you have a nice coordinates, everything is like perfect, you have like this kind of equations which like describe everything. All the functions are given by rational functions. They're not that small, but like they're not that messy also, so you can hope that things are okay. Your oval or ovoid is again a nice projective variety. It sits inside some 7-dimensional space. You can write down the equations for it if you want to. Usually you don't, because like you get crazy if you start looking at them. Oh. Yeah, okay. And now what I want to do is I want to take my picture for my solids and say, put it there and see what's going to happen. So you pick your favorite solid, which you can build out of like going pyramids, which has triangular faces. Okay, I don't remember which one you do. And you just reduce everything to a system of equations. And essentially what you want to say is, okay, I have this system of equations. I want to prove that this system has a solution over my finite field. And you expect to be done like in a day, like just produce the system, check it, and go home. And then you realize two things. There are like two difficulties. I first assumed that this was my main difficulty. So I'm not dealing with standard algebraic geometry. I'm dealing with like algebraic geometry over fields with square root of the Frobenius. So I need to find somebody who knows like how to prove one way and like force him to like change the proof to this language and so on. Okay, I asked a bunch of people. They gave me like a bunch of vague references, which are like, okay, but not extremely useful, like nothing close to what I need to do. And then I realized you can actually very easily modify and like transfer everything to the standard algebraic geometry. You have to just go a little bit deeper and look at the proof of one way and not really just think of it as a completely black box, but like that's more or less doable. But there are a couple of things you have to be a little bit careful. What you have to be careful is really the notion of dimension. The problem is you're dealing with something like algebraic geometry over R. You have a lot of equations which do not have points and do not have any solutions, like even if they're on many variables. And the reason is like if you have a square root of the Frobenius in your field, you cannot have an element which squares to -1. So you have to deal with this thing a little bit. Okay, it's a technical mess to deal with this thing. I figured out how to deal with this thing. It's not really too big of a trouble. But the second problem is actually the more difficult one. So I always assume that like wrong way is like some kind of a black box, like you just apply it and like you're happy, you just, here is the variety, you have more points on it than like you want to, everything is okay. But actually in order to apply this thing, you need to make sure that like you don't have completely obvious obstructions which prevents you from having points. So you need to make sure that your variety is absolutely irreducible. And like this is one of the things you need to check. And like it seems to be a completely trivial thing to do, but like when you start dealing with like that many variables, things are getting completely out of control. And like this is something which I was definitely not able to do on any computer I have access to. And I really didn't want to go to like a really big machines because like things with Grobner bases like do not scale well. If you like the computation for Grobner base is exponential, so if you cannot do it on a small machine, like you have no idea whether like it's feasible to do it on a big cluster or not. So unless like you're confident that like your big cluster can compute something, I'm not going to figure out how to use it and like to make it do something. And there is, at least for me, there is no point of like trying to fight like big clusters and like do computations there. And like one of the reasons is that when you deal with this kind of things, the number of variables like grows very quickly. And one of the reasons it grows is in order to switch from like this algebraic geometry I'm given with where like I have to deal with this kind of square root of the Frobenius to a normal algebraic geometry, I need to more or less like double the number of variables. I'm more or less forced to introduce a new variable which corresponds to x to the theta. So this like increases number of variables to like to something like really like of the order of like 20, 30 and stuff like that. The other thing is like most of the varieties you're dealing with, what's the word for this thing? You get a lot of equations which are cube of something or stuff like this, because like when you start applying like the square root of the Frobenius, like there is a lot of like cubes of stuff like popping up. So the equations you're dealing with are like have like unnecessary high degree, and like this really pushes the degree to something which is a little bit too high and like makes me very uncomfortable to deal with this thing. Okay, so what we did was like we actually found a very clever way to bypass this problem and more or less to avoid checking almost anything. So at the end, like most of the checks I need to do, I can do them practically by hand. I don't really need a computer to do any like computations. I definitely don't need any GRAW03 basis or anything like that. So what's the idea? The idea is the following. Okay, I have some kind of system which like allows me to deduce like Steinberg relations from another one, like in some kind of way. It's not very precise what it is, but one way to formalize it is the following. I can build some kind of like nice variety, and I can think of like points on this variety as like corresponding to some kind of like Steinberg relations. Okay, what do I have on this variety? On this variety, I have like two functions. One is some kind of like projections from this thing to a smaller dimensional one. And this projection saying like, if 2 points have the same projection, then the corresponding Steinberg relations are essentially the same. Essentially, this means like, I'm thinking of the Steinberg relations of like triples of points somewhere, and like they're the same if they correspond to the same element in U. So this function is like taking my triple and computing my element in U corresponding to it. So they're completely the same. And the second one is some kind of like involution, which is built out of like this kind of like LR and all these kind of crazy functions. And if I have 1 point, I can like flip it somehow around and get the stuff corresponding to the flipped point. And what is the nice thing is that these two operations are like, they do not commute. They're very far from commuting with each other. So what I can see is like, I start with 1 point. I can look at like the fiber of the map P to this point. This gives me some curve or whatever I think of it. I flip this thing, I get another curve. Then I get like another, I can like take another fiber to each of these points. This is going to give me like a 2-dimensional thing. I can iterate this thing like 5 times. Eventually, I'm going to cover everything. So what I want to do is I want to say, okay, like these two things, they define me some kind of equivalence relation on my variety, technically on like the points on the variety over my field. And what I want to do is to show that there is only one equivalence class, or like a small number of equivalence classes. Because if I can prove this thing, this means that I can go from any relation to any other relation. And from there, I can say, oh, I can get away with essentially only one relation. You know, there are a bunch of like technical things which I'm completely hiding under the rug. So one of them is like, this does not give me all Steinberg relations. This only gives me like majority of them, say like q cubed minus q squared. Okay, that's easy. Like once you get like to that stage, like it's very easy to take care of like the missing couple of relations. Okay, so eventually, what we need to prove is like a very easy algebraic geometric result, which is the following. Suppose that like I'm given a variety with 2 projections, like from my variety to a smaller dimensional one. And for any field, I can define an equivalence relation on the f points on this variety. I have 2 equivalence relations, one coming from the first projection, the other like coming from the second projection. I can combine them together and get one equivalence relation corresponding to everything. But like this thing really depends on which field I'm talking about. Okay, so what is the stuff we proved? Suppose that we are in this setting. Suppose that like some things are absolutely irreducible. So like my variety needs to be absolutely irreducible. The generic fibers of like the two maps have to be absolutely irreducible. And I don't have an obvious abstraction. At least if I work over algebraically closed field, I only have a single equivalence class. Of course, if this is not the case, there is no hope I can get like a single class over any finite field. And then this implies that over big enough finite fields, you do have a single equivalence class. And the proof is not really very deep. Like what you really do this thing is like you're starting taking some kind of fiber products of your variety with respect to these projections. And what these conditions are here, they actually give you that like each fiber product is absolutely irreducible. There is some kind of general nonsense saying that like if you do a fiber product where like the fibers are absolutely irreducible and the base is absolutely irreducible, then like you have to get something absolutely irreducible unless you have an obvious abstraction, which is not the case here. Okay, so that's essentially like done. So what I need to do is I need to actually check all these three conditions for like the system I'm building here. The first condition is relatively easy to check. My variety V is essentially a four-dimensional space. It's a four-dimensional affine space. Maybe I need to cut some small subvariety there, but like that's not really a big deal. It was like this kind of stuff, which is like, okay, you can take care of it. The fibers of these maps, I can actually compute like what the fiber are. It's not very difficult to see that like after eliminating like a bunch of variables, each fiber is given by a single equation which is of degree 6. And like there are some kind of like very good reasons why the degree is 6 and it's not something big. I can actually like, I know the degree is at most 6 by some kind of like hand-waving arguments. And like also the only thing you need to check is that like some polynomial of degree 6 in like 4 variables is irreducible. Okay, that's something which like my computer can do. I'm pretty sure I can maybe even do it by hand if I try very hard. I'm not sure I want to do this kind of stuff. It's definitely beyond like anything I want to do it. And the last one is that I have one big equivalence class over the algebraic closure. This is really saying that like when you iterate this procedure like 2 or 3 times, it seems that you're getting more than enough points. And actually, we realize that like there is a rational parameterization of something which actually gives me that this kind of thing is true. This rational parameterization is like very easy to construct, and like again like it comes from the fact that like some equation is forced to factor, and like it's of small degree, so like you know one of the factors, so the other factor is also relatively small, and this gives you like whatever you're dealing with it. And so you only need to check that like some map is dominant to make sure that like it's not really going to a smaller dimensional space. So when you put everything together, this kind of completely general nonsense tells you that for large enough Q, like the Lie groups, they do have like a nice presentation which is obtained by doing B and N and adding the central relation. Unfortunately, I really don't want to deal with estimates involving one way and to know like when our bounds are starting to kick in. However, there is something which is like reasonably nice, because like for small enough Q, I can actually produce this variety V, I can produce the points on it, and actually I can check whether I have one equivalence class or not. So I was thinking of doing this thing, and okay, I have been a little bit lazy and didn't have chance to do it. But somehow I believe that like even for like Q equals to 3 to the 3rd or 3 to the 5th, this is going to work. So I actually expect that this is going to give me presentations of all the Lie groups, but like I haven't verified that. So one thing I'm sure is that, okay, Akush like did try this presentation for like the regroup over like 3 to the 3rd, and from what I hear from a bunch of people, he was convinced that like this presentation gives an infinite group. Now, what I suspect is that in order to, when you start doing costed enumeration, like your cost enumeration actually explodes, and like you really need to go very, very far before actually seeing these kinds of consequences which like are hidden here. So what I really want to do, but like I need somebody who actually knows Magnum very, very well, is to take Magnum and say, okay, like I see that you cannot really show me that like this presentation gives me a finite group because like you run out of memory. But if I nudge you a little bit and like force you to do the computation in this correct way, you should be able to do it. But I have no idea how to like force Magma to do stuff which like that. And okay, I want to stop here, and again, like thanks all the organizers and all of you for being here. Sure.
So you said that at least in principle there is a relation between existence of short presentations and counting groups, finite groups by order.
Okay, there is a relation between having a presentation with a relatively small number of iterations. And I think relatively small, maybe Martin, you can correct me, something like cube root of the size of G, which on the scales of what I'm doing, it's enormous. Yeah. Even like essentially taking all this time preparation is enough for this kind of picture. So I think, is this what we are talking about? I think for this application, like it was known way before that, and like we didn't, one doesn't really need to have anything close to that, or even for like symmetric groups, like you can more or less get away with like a standard Cox representation on like transposition and like n-square relations. For rank 1 groups, like you can start with the standard time representation, but I'm not completely sure what are the bounds which are needed, but like they're relatively weak. Okay, I think that was what we were talking about. Sorry.
And how is the idea implemented? Are you using triangular representation from the ones themselves?
I'm not sure I understand the question.
So why is having two relations then useful?
Okay, so okay, if you want to do like some kind of recognition of like groups, like definitely having fewer relations to check is like significantly faster, especially if these relations are like much more explicit. Of course, like there is a trade-off between like a few relations and like easy relations, which like you can easily check and easily store, and also there is trade-off between natural generators and some kind of completely crazy generators you need to deal with. So if you want to go to like really short presentations, you have to go to some generators which are extremely unusual, and like you have to pay a lot of price between like switching from one generating set to another generating set. I think the statement that like a group has like a presentation with a small number of relations, this is independent on the generating set. Like if you switch the generating set to another one, the number of relations is not going to change by much. Like you probably need to add a number of generators or something like that. However, the rank of the relations can actually change significantly. So having a short presentation, like short of like really, here we're talking the size of like logarithm of n for the symmetric group, this is definitely not possible for any generating set. You have to start with a very particular generating set for this thing to work. And I think that's Iman's main complaint is like, we have this presentation on some completely crazy generators, which like he barely understands, and like he really doesn't want to go to them and to switch back and forth to figure out what's happening. So whether this thing actually has applications for like computational people, yes and no. It was, I think, like having like a bound number of iterations is useful, but making them that short, I think it's a little bit too extreme, and like they don't care. It's like the cost of going there is too much. Yeah, they're completely explicit. You just take a presentation of the Borel, which is like you need to fix a model of your field, like so you have to fix like a generator of the field and all this kind of stuff. You need to take the generic formulas for like the multiplication in the unipotent group, which like you open the book and like you just copy them, you implement them like in your system. That's what more or less you do. Okay, you add the action of the torus, which again is like given by some nice formula you implement in the same way, and you just add one relation corresponding to the central Steinberg relation, which is really like things inside like the group over F3 to glue everything together. And that's it. You don't need to do anything else.
The problem is whether that really is a presentation of a finite group.
Yeah, okay. These are relations which are definitely satisfied in the group. And like what this claim is, they actually gives you a presentation of the group, not of something much bigger. Even though like if you put them on a computer, it seems that like they give you something much bigger. Okay, I haven't put them on a computer, so I don't know. And I'm not the kind of person who gets like his hands dirty with computers, but people told me that like that's what happens.
You prove that it doesn't happen.
I prove that like this presentation works. What I'm saying is that like if you take this presentation and put it on like your standard computer, the computer is probably going to think forever and say like, it seems that it's infinite, but I have no idea what's happening. Maybe if you have infinite amount of memory and infinite amount of computer time, like the computer eventually is going to tell you that it's finite, but I'm not sure that you're patient. Yeah, that's like because like it starts expanding too much. Eventually, it's going to terminate. Of course, like it's possible that like I have no idea what I'm talking about, and there are like 30 mistakes, dips in this kind of stuff. If this is the case, of course, it's not going to terminate. But like, I think the proof is like reasonably robust. Like I have like it doesn't require like any technical computations. It doesn't require anything like we see that like these kind of things do happen. So like this is like something which proceeds. Like things are like relatively okay, like even if like you start missing some stuff. So for example, I don't really need like this variety V to be like rational and like isomorphic to a 4-dimensional space. The only thing I care is that it's irreducible. So, you know, this kind of stuff like are reasonably rigid. I suppose I'm doing something very similar. I haven't talked to Tom about this kind of stuff. Maybe if I talk to him, he's going to say, yeah, I have done exactly the same thing. I just asked a bunch of people, and they said, like, sure, like, Wang-Wei should work in this kind of context. There is no obvious problems, but I cannot give you a reference where it's done. So eventually, I start like asking people, and like, you just go to a standard proof of Wang-Wei using like a tau cohomology, and like you say, okay, like this proof actually works in this setting, like you don't have to modify it at all. So I'm not using anything fancy. I'm pretty sure like Tom is like way more careful person than me. So if he have done some stuff there, his stuff is way more correct than anything I have done. That's correct, but like I was not able to extract anything out of Khrushchev's paper. I'm pretty sure I'm not the only one who has trouble extracting information from these papers. So there was like, okay, I'm not claiming that like the stuff that Wang Wei works in this context is like very deep, new and stuff like this. I'm pretty sure a lot of people know about this thing and they have done it. I just needed something a little bit more precise. I wanted to be able to control when these things at least have some kind of vague idea, like to be able to bound for which Q things are going to start kicking in. So I needed to do something a little bit more careful. So one thing which like came out of this thing, and I find it a little bit surprising, is that the error term of Wang Wei is not the one you expect. So normally you expect the error term to be like q to the minus 1/2, but in this case actually the error term is q to the minus 1/4. And the reason for this thing is like you really have to double all the dimensions, so you're doubling the dimension, and like since you're doubling the dimension, like 1/2 becomes 1/4. That's roughly what's happening. Okay, is this thing very deep? I suppose no, but I find it a little bit surprising.